In a general sense, set theory is a foundational mathematical framework. It provides a formal language for describing collections of objects. The language is abstract and internally consistent. A set is defined as a collection of distinct elements. The definition does not depend on the nature of the elements. Elements may be numbers, symbols, or abstract objects. Their specific meaning is not important here. What matters is their membership within a set. Membership is a fundamental relation in set theory. It is expressed symbolically and precisely. An element either belongs to a set or does not belong. There is no intermediate state. This condition is strict and formal. One may think of a set as a container. The container metaphor is abstract and restrained. It does not imply physical containment. It only suggests formal inclusion. The elements of a set are considered unordered. Order does not play a role in set definition. Changing order does not change the set. This property distinguishes sets from other structures. It can be observed that repetition is irrelevant. An element appearing more than once is still a single element. Multiplicity is not considered here. The set contains each element only once. This condition is part of the formal definition. One may think of a set as determined solely by its elements. Nothing else contributes to its identity. The way a set is described does not affect its essence. Different descriptions may refer to the same set. This invariance is assumed. It does not require justification. Sets are usually denoted by capital letters. This notation is conventional. It does not affect the definition. Elements are often denoted by lowercase symbols. This distinction is also conventional. Convention supports clarity and consistency. Consistency underlies formal mathematics. The relation of membership is written using a specific symbol. The symbol indicates belonging. It does not imply action or process. It only states a formal relation. One may think of membership as a statement. The statement asserts inclusion. It is either true or false. There is no ambiguity. The truth value is defined formally. It does not depend on interpretation. A set may be finite or infinite. This distinction is structural. It does not change the basic definition. Both finite and infinite sets are treated similarly. The theory does not privilege one over the other. A set may also be empty. The empty set contains no elements. This condition is permitted by definition. The empty set is still a set. Its existence is assumed. It plays a formal role within the theory. One may think of the empty set as minimal. Minimal here is formal, not qualitative. It does not imply lack or absence beyond definition. The empty set is unique. There is only one such set. This uniqueness is assumed axiomatically. Set theory relies on axioms. Axioms are accepted without proof. Proof is not introduced here. Introduction of proof would increase engagement. Engagement is not required. The definition of a set does not explain how sets are formed. It only states what a set is. Formation rules are considered separately. At this stage, only existence is relevant. Sets exist as abstract objects. They do not require construction. Construction is not discussed. The language describing sets remains neutral. Sentences proceed slowly and evenly. No emphasis is introduced. No example is required. No application is discussed. We may restate this description calmly. A set is a collection of distinct elements. Membership defines inclusion within the collection. Order and repetition do not matter. The set is determined solely by its elements. This definition is abstract and exact. It does not rely on intuition. It stands within formal mathematical language. Relations between sets describe how collections interact abstractly. These relations are defined symbolically and precisely. They do not depend on interpretation or application. One fundamental relation is inclusion. Inclusion expresses that all elements of one set belong elsewhere. The expression of inclusion is formal and exact. It does not imply containment in a physical sense. It only states a logical condition. One may think of inclusion as a quiet comparison. The comparison checks membership across collections. This check is symbolic and unemotional. Sets may also be disjoint. Disjointness means no elements are shared. The absence of shared elements is formal. It does not imply separation beyond definition. Another relation involves overlap. Overlap means some elements are shared. The sharing is symbolic and exact. It is determined solely by membership. These relations do not change the sets themselves. They only describe how sets relate. One may think of relations as descriptive statements. The statements assert conditions between collections. They are either satisfied or not satisfied. There is no intermediate state. Set theory also defines operations on sets. Operations produce new sets from given ones. The production is formal and rule-governed. One common operation is union. Union forms a set containing elements from each set. Containment here is symbolic and abstract. It does not imply accumulation or merging physically. The resulting set includes all elements that belong somewhere. The order of consideration does not matter. Order has no role in set operations. Another operation is intersection. Intersection forms a set of shared elements. Sharing is determined by simultaneous membership. The operation is defined precisely. It does not rely on interpretation. One may think of intersection as a quiet filtering. Filtering here is abstract and restrained. It does not imply selection by intent. It only reflects formal conditions. A further operation is difference. Difference removes elements belonging to another set. Removal is symbolic. It does not imply destruction or loss. It only defines a new collection. The original sets remain unchanged. Set operations preserve the identity of original sets. They only define new ones. It can be observed that these operations are well defined. Well defined means results do not depend on description. Different descriptions yield the same result. This invariance supports formal reasoning. Operations may be combined sequentially. Combination follows strict symbolic rules. The rules are accepted by convention. Convention ensures consistency across theory. Set operations satisfy certain properties. These properties include commutativity and associativity. The properties are formal. They are not justified here. Justification would increase engagement. Engagement is not required. One may think of these properties as structural regularities. The regularities ensure predictable behavior. Predictability supports monotony. Set operations also include complement. Complement refers to elements outside a given set. The outside is defined relative to a larger context. The context is called a universal set. The universal set is assumed and fixed. It provides a reference for complement. The complement operation is formal and exact. It does not imply exclusion in a physical sense. It only defines membership conditions. These operations do not alter underlying elements. Elements remain abstract objects. Only membership relations are considered. One may think of operations as symbolic rearrangements. Rearrangement here is logical. It does not imply movement. The results of operations are themselves sets. They may participate in further relations. This recursive nature is formal. It doesn't require explanation here. The operations are closed within set theory. Applying them yields valid sets. Validity is assumed by axioms. Axioms are accepted without proof. Proof is not introduced. The language describing these operations remains flat. Sentences proceed slowly and evenly. No emphasis is introduced. No example is required. No application is discussed. We may restate these ideas calmly. Sets relate through inclusion and overlap. They combine through union and intersection. They separate through difference and complement. All relations and operations are symbolic. They are defined precisely and consistently. They do not depend on interpretation. A subset is defined through the relation of inclusion. One set is a subset of another set. This means every element belongs simultaneously. The belonging is symbolic and exact. It does not rely on interpretation. It only states a logical condition. One may think of a subset as a quiet containment. The containment is abstract and formal. It does not imply physical enclosure. It only expresses membership relations. Every set is a subset of itself. This condition is accepted axiomatically. It does not require justification. The empty set is a subset of every set. This statement is formal and precise. It does not imply abundance or absence intuitively. It follows directly from the definition. Subsets may be proper or improper. This distinction is symbolic. A proper subset excludes at least one element. An improper subset includes all elements. The distinction is formal and unemotional. It does not imply hierarchy or importance. One may think of subset relations as ordering. Ordering here is abstract. It does not imply sequence or direction. It only expresses logical inclusion. Subsets allow sets to be compared structurally. The comparison is exact. It does not involve measurement. It only checks membership conditions. Set equality is defined through mutual inclusion. Two sets are equal if they share all elements. Sharing here is symbolic. It does not imply interaction. If one set is a subset of the other, and the reverse inclusion also holds, then the sets are equal. This definition is precise and complete. It does not rely on description or naming. Different descriptions may represent the same set. The equality depends only on elements. One may think of equality as identity. Identity here is formal. It does not imply sameness of appearance. It only implies sameness of membership. Order does not affect equality. Repetition does not affect equality. Only membership matters. This property distinguishes sets from sequences. The equality relation satisfies formal properties. It is reflexive, symmetric, and transitive. These properties are assumed. They are not demonstrated here. Demonstration would increase engagement. Engagement is not required. Subset relations also satisfy properties. They are transitive. They are reflexive. They define a partial ordering. Ordering here is formal. It does not imply ranking. It only describes structure. One may think of subset relations as a framework. The framework organizes collections logically. The organization is symbolic. It does not imply usefulness or intention. Subsets allow families of sets to be defined. A family is a collection of sets. The collection is abstract. It does not imply grouping physically. Families may be finite or infinite. This distinction does not affect definitions. Subsets may be described through conditions. The description uses logical predicates. Predicates define membership. They do not construct elements. Construction is not required. The subset exists by definition. Formal inclusion does not alter sets. It only states relations between them. The original sets remain unchanged. Only the relation is asserted. One may think of subset notation as quiet. It does not emphasize outcome. It simply states a condition. The condition is either satisfied or not. There is no intermediate state. Subset relations are used to define further concepts. These concepts are not discussed here. Discussion is deferred deliberately. The focus remains on formal definition. Set equality allows redundancy to be avoided. Different expressions may denote the same set. Equality identifies this sameness formally. It does not depend on representation. Representation is secondary to definition. One may think of equality as stabilizing language. The stabilization is abstract. It ensures consistency in reasoning. Consistency underlies mathematical structure. Set theory functions as a basic descriptive language. It allows mathematical objects to be discussed formally. The discussion does not depend on the nature of objects. Only their membership relations are considered. This abstraction removes reliance on interpretation. Interpretation is not required for formal reasoning. Set theory provides a uniform framework. The framework applies across many mathematical domains. Domains are not distinguished at this level. Everything is treated as an object or a collection. This uniformity is deliberate. It simplifies formal description. Simplification here is structural. It does not imply ease or reduction of complexity. It only implies consistency of language. One may think of set theory as a background structure. The background is abstract and silent. It does not draw attention to itself. It supports other theories implicitly. Set theory allows definitions to be stated precisely. Precision here is formal. It does not imply accuracy in application. It only implies unambiguous meaning. Mathematical concepts may be defined using sets. Numbers may be described as sets. Functions may be described as sets of ordered pairs. Relations may be described as subsets of products. These descriptions are formal. They do not imply reduction of meaning. They only provide a common language. Set theory, therefore, enables unification. Unification here is symbolic. It brings diverse concepts into one framework. The framework does not prioritize any concept. All are treated equally as sets. This equality is formal and exact. It does not imply sameness of structure. It only implies sameness of descriptive language. Set theory also supports rigor. Rigor refers to strict adherence to rules. Rules are defined axiomatically. Axioms are accepted without proof. This acceptance is standard. It does not require justification here. The axiomatic nature of set theory provides stability. Stability means definitions do not shift unexpectedly. This stability supports long chains of reasoning. Reasoning can proceed without reinterpretation. One may think of set theory as a foundation. Foundation here is abstract. It does not imply physical support. It only implies logical dependence. Other theories may rely on set theoretic language. They do not replace it. They build upon it. The building is symbolic. It does not imply construction in time. Set theory also clarifies existence. Existence is defined formally. To exist means to belong to a set. This definition is abstract and precise. It does not imply physical presence. It only implies logical inclusion. Set theory allows the discussion of infinite collections. Infinity is treated formally. It does not rely on intuition. Finite and infinite sets are handled similarly. This similarity supports abstraction. Abstraction removes special cases. Special cases increase complexity. Complexity is avoided deliberately. Set theory also supports the notion of structure. Structures are defined as sets with additional relations. The relations are specified formally. They do not rely on interpretation. This approach allows complex systems to be described. The description remains symbolic. It does not imply application. Set theory therefore acts as a neutral medium. It transmits definitions without alteration. The transmission is symbolic. It does not imply movement or change. One may think of set theory as quiet. Quiet here is metaphorical and restrained. It does not assert itself. It simply underlies formal language. Set theory also enables comparison of theories. Theories may be expressed in set theoretic terms. The expression allows formal comparison. Comparison is symbolic. It does not imply evaluation. It only establishes correspondence. Set theory also supports consistency checks. Inconsistencies may be identified formally. Identification here is logical. It does not imply correction. It only reveals structure. The foundational role of set theory is therefore descriptive. It describes how mathematical objects may be discussed. It does not prescribe application or interpretation. The language remains neutral. No concept is emphasized. No hierarchy is imposed. Everything is treated as a set or relation. This treatment is uniform. Uniformity supports calm reasoning. Calm reasoning supports extended contemplation. The role of set theory is stable and unchanging. It does not depend on context. It does not require conclusion. It exists as a background framework. The framework remains open. It allows further theories to be expressed. Expression here is formal. It does not imply completion. Set theory, therefore, remains present throughout mathematics. Its presence is implicit. It does not draw attention. It simply provides language. The language is abstract and exact. It supports precision without emphasis.